Hello?
Hi. Hi, it's Mrs. Ross's Erica. How are you?
I'm I'm good. Is Adam having trouble getting on or something?
Everybody is. The team viewer thing that we use actually just dropped. And I
Oh,
can't reconnect to it. So I just thought I'd try an alternate method. So sorry if it called on your phone. I was trying to figure out something. Everybody had Gmail, so I was like, oh, maybe we can connect on Gmail.
okay. Well that's fine. He can just use my phone or is everybody on already?
Okay. Yeah, and we'll see if some other people can connect too, because like I said, it just kind of dropped for me. So sorry about that.
No, that's okay. You're gonna have to use my phone through this thing.
Hello.
Oh, Adam talk. Yeah, we're here.
Okay, I just want to make sure. All right. So Adam, I was on TeamViewer and then it just like randomly dropped in the middle of it and now I can't reconnect. So I'm thinking it's an issue with TeamViewer. Um, so hopefully I sent out an invitation to everybody through Gmail, so hopefully they can connect.
Oh, okay.
Yeah.
Will they be connected on the same live viewing?
Yeah, they should all be together here. I've actually done it with my geometry class and it's worked. It's just if everybody knows to check the link. So I'm trying to contact a couple of people. Somebody texted me here, so.
Okay. I'm gonna go get my charger with my phone.
Adam, did you have any questions you wanted to go over?
No, I don't think so.
Gotcha. How do you feel about chapter 6?
I don't know.
I think he's still trying to wake up some. Where's your plug at?
All right, I'm gonna kind of flip over here. I don't know if, let's see. Sometimes technology works great and sometimes it just doesn't want to work. So let me email everybody the link too.
You have it?
Okay, what are you doing?
You need extension cord?
Sure.
What in the world? The cord must be on the bed. Let's see if that is attached to the bed. It gets stuck down in there somehow. I was getting ready to move the bed.
All right, Adam, we're not having much much luck getting everyone on here.
Oh, there's somebody else.
Hey, Sarah.
Hey,
How are you?
good.
Good. That was crazy. The team viewer just like dropped right in the middle of it.
I was so confused. I was like, what happened?
Yeah, it just dropped right in the middle. Let me send this link to Aiden and Sarah and see if they can get on. Yeah, so let's see if we can get everybody connected.
Okay.
Sarah, did you have to like download anything to do Google Hangouts or anything? Or did it just kind of...
No, you just like sent me the invite and then I just pressed join.
Okay. I'm hoping Jennifer can join since she had the 2 questions we wanted to do.
Yeah.
So hard when it's... Technology is not working.
Yeah.
All right, guys, we'll give them like 3 or 4 more minutes and then I might just... I don't know. I could go ahead and do those 2 problems so Jennifer can watch them later. Sarah, did you have any? You said you didn't have any questions, right?
Yeah, I don't think so.
Okay.
Actually, could we do number 33 from 6.4?
Yep. That's actually the one that I was just starting to do with on the other call, right? Is that right?
I don't remember.
Okay. Why don't we go ahead and get started and hopefully they can connect in. You said 33, right?
Yeah.
Okay. Hello, Aiden. All right. I think we're going to go ahead and get started. I think you should be able to see my screen by now. Is that right? Can everybody see my screen?
Yeah.
Okay. I think I can also turn on a chat in case you don't have a mic. Let's see. I think there's a chat thing here somewhere. Chat, if I want to chat. Oh, here we go. There we go. I can chat over here to the side. Okay. Sorry about the technology thing. I think it was just TeamViewer. Like it just dropped and now I can't reconnect to it. So, okay. So we were doing number 33, which is in 6.4. And we were trying to tell if these two vectors are orthogonal, parallel, or neither. Okay. And so we are going to use our angle between two vectors to figure out what the angle is, and then depending on what the angle is, then that will tell us if they are basically perpendicular to each other, if they are parallel to each other, or if they are neither of those two things. Okay. So this looks like a fun math challenge, right? Let's see. All right, so we want to do this. So this is our two vectors, and then over here on the right-hand side, Jennifer, you're here, yay. Everybody figured out how to get on here. I'm sorry for the team viewer issues. Okay, so we have the two vectors, and then we have our angle between the two vectors, right? And so now we're just going to go and do each part of this formula. So we're going to do u dot v first. You guys are going to have to check my math. So we're going to have negative 12 times 1/2, right? And then we're going to have, not comma, plus 20 times negative 5/4. Okay, so we end up with negative 6 plus negative 25, I believe.
I think
Right.
it's 30, not 20.
It is 30. Thank you. That would have been really bad. Because then we would definitely not get whatever the solution is. So this is 30. So then when I do, let me erase here. My eraser app. Erase that. Thank you. Okay, so 2 goes into 4 2 times and goes into 15, or goes into 30. 2 goes into 30 15 times. There we go. That's what I was trying to say. So 15 times 5 is 75 over 2. Oh, fun with fractions, right? I always love it when we have fractions in our vectors. So I'm going to make this negative 12 over 2 plus negative 75 over 2. And I end up with negative 87 over 2 for my dot product of u and v. Right? Okay, so now I have to do the magnitude of u and the magnitude of v. So I'm kind of thinking that, well, in my head, because I did u dot v and I get a number here and I didn't get 0, then I'm already ruling out that they're orthogonal, right? Because in order to have a right angle, the cosine of 90 degrees of the cosine of 90 degrees equals 0. So u dot v would have had to have been 0 in order to have perpendicular angles. So I'm kind of ruling that out in my mind right now. Okay, so now I need to figure out the magnitude of u and the magnitude of v. So the magnitude of u is going to be negative 12 squared plus 30 squared, all under the square root. Okay. So does that work out nicely for me? Well, let's see. Negative 12, or 12 squared plus 30 squared gives me 1,044. Square root. We're just going to leave it like that. Okay. And then v, oh, we get to do fractions with square, taking squares, right? So we have 1/2 squared plus negative 5 over 4 squared. And then take the square root of that whole thing. So we end up with 1/4 plus 25 over 16. We can change 1/4 to 4 over 16 just off to the side here. So we end up with 29 over 16 square root. Okay, everybody, same so far? You're like, there's no way that this is going to be parallel, but let's see. Maybe this might be parallel. Let's see. All right, so now I'm going to plug the whole thing in, okay? So I get the cosine of theta equals negative 87 over 2 divided by the square root of 1,444 times the square root of 29 over 16. Okay, let's see. Now, where do we want to go from here? We could try to simplify our square roots a little bit. Ugh, I'm going to use a calculator for this because has anybody done this and gotten a value that they think would be helpful? No, okay. So one option is if you don't even want to mess with any of this, you could, as most works for us, we could just go straight and plug in the whole thing. So let's kind of do that first to see if we're in the right direction. So I got way too many parentheses going on here. So that's my top of my fraction, and that is divided by the square root of 1,044 times the square root of 29 divided by 16. Okay, so when I plug this big crazy thing into Desmos, I end up with -1. So somehow we should be able to reduce this down to 87 over 2, which is kind of crazy to think about. So I'm guessing if we do 1,044 times 29, and then we divide out 4, that this is the square root of 87. So let's see, what is 87 squared? Okay, so if, what I was kind of doing here, quick math off to the side, as I was saying, okay, if we want this radical at the bottom to end up being 87 over 2, then what would these numbers have to work out to be? So it turns out that if you do, I don't know, does that make sense? Do you want me to see how you do it? So, oh man, I didn't mean to do that. Bring that back up. Basically, if we multiply this out, you're going to be able to get this reduced down to 87 over 2. And I can show you how to do that if you want, but I think you guys would probably figure that out. So if we find that the cosine of theta is -1, right, that means that our angle is 180 degrees between our two vectors. And so if our angle between the two vectors is 180 degrees, then those vectors are going to be parallel to each other. All right, what do you guys think? Does that make sense? One other quick thing, one quick check that you can always do is to throw these points into Desmos or your graphing calculator, either one. So if I plug in my vector u is -1230, and you can hand graph these too, right? And my vector v is 1/2, comma, -5/4. Okay, and then I'm gonna have to zoom out, obviously. But you can see that it's plausible that these vectors are, if they're looking from the origin, that these vectors are parallel to each other, just going in opposite direction. That makes sense? Yay, vectors. That's right. Jennifer, you're my trigonometry champion now. All right, Jennifer, I lost the other question in 6.5 that you asked when TeamViewer crashed on me. So remind me what number in 6.5? Number 25. Okay, so in 6.5, we kind of jumped, what do you want to call it? Jumped concepts a little bit, and we are still with trigonometry, so we didn't jump that far, but we're talking about graphing and we're talking about graphing complex numbers. So we have a real component and an imaginary component. And then we also talked about how we can rewrite complex numbers in trigonometric form. And so that's what number 25 is how do we rewrite the complex number -7 + 4i in trigonometric form. So again, just another way of writing the same thing, but we're going to use our trig functions to do that. No, I don't want to save. That's what I said, but I didn't. Okay, so we have, make sure I write it correctly, -7 + 3i, okay? Represent the complex number graphically and then find the trigonometric form of the number. Okay, I'm going to spare you guys from my drawing. And I'm going to cheat a little, and I'm going to use Desmos. Even though this is a coordinate plane, and what we're talking about, a complex plane, I don't think it's that far of a jump to say, oh, if I have a real component of -7, that is like my x component of -7. And my imaginary component is +3. And then I can just check out my graph here, right? So my vector is in the second quadrant, right? And so that kind of just gives me a hint as to what kind of angle that I'm going to be looking for. Am I going to be looking for, you know, something that's between 0 and 90 or 90 and 180? I'm going to be looking for something in that range, right? Okay, so then the next part is to actually convert it to our trigonometric form, okay? So the formula for trigonometric form is that we have r times the cosine of theta plus I times the sine of theta. Okay, and our r represents basically like the magnitude of our complex number, right? So to find r, we're going to do the real part of our number squared plus the complex part squared, and then take the square root. So it's kind of, I mean, it's just like distance formula, Pythagorean. They're all related to each other, right? So for this case, we're going to do -7 squared plus 3 squared square root. So 49 plus 9 square root, or the square root of 58. Everybody okay with that? It's exciting, right? Okay. Guys, did I totally write down the problem wrong again? I did. You're gonna have to watch me today. This should be 4. Like looking at my notes when I did this problem, I'm like, oh, that's not right. So that's going to change this value and this value. Apparently, I just want to do all the problems with different numbers today. Oh, look it. If I would have looked in the chat, there, that's what you said, Jennifer. Okay, let me pay more attention to the chat. Okay, so we have 4 squared, 16, and this becomes 565, right? Is that better? Okay, so then when we go to find the theta, the angle, okay, so think back to unit circle and we first started out and we're like looking at this unit circle like, what is this going to do this to us, right? If we think about our theta, okay, if we find the tangent of theta, okay, that's equivalent to our complex part of our imaginary part of our complex number over our real part, right? So complex part, or imaginary part over real part. And so that's just kind of back to our thing, right? So we have the complex component is 4 over -7. So 4 over -7 is not on our standard unit circle, right? I'm trying to write it a little bit nicer, but it's not on our unit circle. So we're just going to have to take the arc tangent and figure out what the value is. Okay, so if I pop over to Desmos, I get okay, so I end up getting -0.51914, right? Now, does that seem like that's the value that I'm talking about? No, right? Because -0.159 is going to be down. It's actually going to be going this way. And if I switch this, sometimes it's helpful to switch to degrees. So basically they're saying that this is at -30 degrees. So remember your calculator, when you take a, when you take the arc, sine, cosine, tangent, you're not always going to end up with the exact value. You might end up with a value that is pi or 180 degrees off because there's only a limited number of values that your calculator can calculate. So because of that, what I'm going to do is I'm going to, it doesn't matter if you want to leave it in degrees or radians. So if I wanted to leave it in degrees, I would say, well, what is 180 degrees plus, -29.74488. So 50.225 degrees. So does that seem more reasonable for my angle? So I think that seems more reasonable, right? Yep. Maybe. I think it seems reasonable. Okay. Let's see. So we can say that theta equals 150 degrees, what was it? 0.44? 0.25. 0.255. Okay. Or if you really like radians, you could leave it in radians. So remember, I'm going to write off to the side, if you did it in radians, when we evaluated, let me just switch my calculator here. if I was in radians and I have negative 0.519, then I need to take that value and add pi to it, right? Maybe plus pi. Okay, so I get 2.622 radians, which again puts me in the right realm. It's between, you know, it's not up to pi yet, but it's in that right realm. So if I want it in radians, I could say 2.622. So then when you're writing the trig form of these complex numbers, they don't look as pretty when you don't get to write on the unit circle, right? So if I would write the trig form in degrees, oh, okay, I would write square root of 65 times the cosine of 150.25 degrees plus I times the sine of 150.25 degrees. And then, of course, if I was writing in radians, I would just write the same thing, but I would use 2.622 as the value. Okay? Sure. Any other questions on chapter 6? No questions? All right. We have like 13 minutes. I'm not going to use all 13 minutes, but I did want to give you like this slight little taste of 7-1 to bring out, like, dust off your cobwebs from Algebra 2 and talk about systems of equations, because we have, and two reasons I want to do this. One, I think it's helpful to see it twice. If we talked about it today and Monday, that's great. Two, we have our nice graphing tool that I can pull up. So again, I'm going to try to just give you a 9 minutes so you can get out early. 9-minute dust up on our next section. So after you complete your chapter 6 test, you're kind of leaving the land of trigonometry and coming back to the land of algebraic functions. And chapter 7, the first thing that we're going to start off with is solving systems of linear equations. Okay, and actually we're just going to start talking about linear systems and what those are. So, no, okay. 7-1 is solving just systems of equations. 7-2 is linear systems of equations. I apologize. So the difference between that is obviously in 7-1 we're just talking about any system of equation, and 7-2 we're talking about linear, so we're just talking about lines. But what is a system of equation? It's just basically two or more equations that are grouped together. And what you're trying to do is not just solve the single equation, but you're trying to solve for all two, all three, all 6 equations, however many equations you have. You're trying to find the value that makes all of the equations in the system true. Okay, so I think most of you have done some of this work in Algebra 2, but it's always good to kind of start back with where we're at. So let's start with a really kind of easy system here. Trying to look for one here. This is number 16 from your homework, but if you just want to watch today, we'll do more on Monday. So these two systems, or these two equations that are in the system, happen to both be linear. So that makes it easy. But we have 6x minus 3y minus 4 equals 0. And we have x plus 2y minus 4 equals 0. Okay, so these are two equations. They both happen to be linear equations, and they're in a system together. So when we're looking at this, we're not trying to just solve this equation for an ordered pair of x and y that's true, or this equation for an ordered pair of x and y that's true. We want to find which x and y is true for both equations. Okay, so we want to solve both equations and find which value or values are true for both equations. Now, in linear equations, there's either one solution, many solutions, infinitely many solutions, or no solutions. When you get into like a quadratic or higher equation, then you can have more than one x and y value that may solve your equation. And we'll talk about kind of how we do that. So does this look familiar to everybody-ish? Solving for x and y. Yep. All right. Jennifer remembers it. All right. Are you guys groaning or excited? This is like the algebra section, right? Where you really do lots of problems. Does anybody remember some methods for how you can solve systems of equations? Substitution, Aiden, absolutely. That's a huge one, and that's one of the ones in 7.1.
And elimination.
Yep, elimination, that's another one. There's substitution, elimination, and then kind of the easy one, I like to call it, the less writing method is graphing, right? So don't forget graphing. That's also a valid way to solve systems of equations. Now, of course, sometimes we're asking you to do different ones. So I just wanted to pull that up since we have Desmos right here. Let's start with the easy one, right? If I graph two linear equations, okay, if I graph 6x minus 3y minus 4 equals 0, and I graph x plus 2y minus 4 equals 0. Now, if you have a TI calculator and you're trying to graph this, what do you have to do before you can just graph it? Desmos lets you write in any form, right? But for a TI calculator, you're going to have to get this into y equals, right? Y equals form. So this is a nice graph of two lines that we have. And the value in which they're both true is where they intersect, right? Our intersection point. So it looks like for this one, it's 4/3 over 4/3. Kind of spoiler alert before we got there. So this would be an example of a system of equations. This particular one is a linear system of equations that has one solution, right? And we can also, we'll do some substitution to do that too. Let's see if I can manufacture this a little bit. I'm just going to go easy here, guys. I'm going to rewrite it in slope-intercept form, and then you guys can really see. So this is completely different equation. So what if I have y equals 2/3 x plus 6, and I have y equals 2/3 x, 2/3 x plus or minus 1. So I switched over to slope-intercept form because that's really easy to see. But if I have these two equations as a system of equations, right, when I graph them, do I ever have an intersection point? Nope, right? They have the same slope and they have different y-intercepts. So these two lines are never going to intercept each other, right? They're never going to have an intersection point. So if you have a problem like this, you are going to have no solution, right? So there's most cases there's one point of intersection or multiple points of intersection, and that just means that there's one value that works, right? Sometimes we have no solution because our two equations never have any values that make both true at the same time. Okay, and there's some examples of that, like that we'll do that are not even linear equations. Sometimes we have no solutions. What is the other case, just to kind of go through the simple cases for linear? What if these actually were, let's write 4, 6 plus 6. Right, so these were my two equations. and I actually recognize that, oh, these are the same equation, they're just written slightly different, right? In this case, we would have, do you remember what we call this? Infinitely many solutions. So anything along this line is a solution. So we have infinitely many solutions when we have two equations that are actually the same, that are masked as different in our system. So that's kind of a review of that. If going back to that original number 16, we only have a minute or two left, so I'm not going to go through all the steps, but I do want to just mention the steps if we want to use substitution. So if you want to use substitution to solve your problem, the steps are, number one, you solve one equation for one variable. Okay? So maybe I solve my second equation for x, and I say x equals 4 minus 2y. Okay? Then I substitute that solved equation into my other equation. So I substitute it in. Okay? I'm not going to do this because we're running out of time, and then I solve that equation. So what that does by substituting one equation into the other is that when you start with a system of linear equations, you have two equations and two variables, right? And when you substitute one into the other, then you end up with one equation with one variable that you're able to solve for. So we solve one equation for one variable, we substitute it in, then we solve the equation. So in this case, we are going to be solving for y, equation for y, okay? Once we find y, we back substitute and find x. And then we check our work. So I'm sure you guys did this a lot in the past, but I just thought, oh, we have a few minutes here, we'll just update on that. So much more to come on 7.1. Don't worry about starting the homework on it or anything. I just thought since we had a minute or two, we'll pull that back out of our brain and get ready for Monday. So if anybody has any questions on chapter 6, let me know, or anything else, just let me know. Thanks, guys. Thanks for being flexible with the technology. Sorry that was crazy.
Thank you.
Bye. Thanks. Bye.